How about going deep, deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding, but there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day? Brace yourself. You're about to hear one of the most unusual sounds ever. It's come from space, and it's the sound of two black holes colliding. But first things first. Our ears are designed in a special way, which helps us translate sound waves. But these sound waves become mute once the medium they're traveling through comes to an end. It happens when, for example, the atmosphere of Earth gives way to the vastness and emptiness of the cosmos. At the same time, there are some sound waves that can move even through a vacuum. And we can translate these vacuum-friendly waves into sounds our human ears can hear. That's kind of like radio transmissions work. Over the past few decades, people have sent quite many satellites to the far reaches of the solar system, and even beyond. These spacecraft are equipped with sensors designed to hear such things as radio and plasma waves, flowing freely through interplanetary space. These instruments are crucial for research and communication reasons. An additional bonus is that now we can finally hear different kinds of space waves as audible sounds. The results are often ear-splitting sounds, and sometimes audios are downright scary. Usually, when two black holes collide, they don't produce a sound. And still, thanks to modern technologies, we can now listen to this terrifying cosmic event. Do you hear it? This chirping sound is the sound that two black holes produced while slamming into each other around 1 billion light-years away from our planet. Interestingly, the tone of the sound rises when the holes spiral closer to each other and stops abruptly when they eventually merge. Now, do you hear that long, low buildup? It means that the merger is quite slow, more sedate, and the black holes taking part in this event are relatively lightweight. A more abrupt chirp is a sign of a fast merger, where the black holes are rather large. For example, the pair that produced this sound combined and created one black hole more than 80 times the mass of the Sun. Since each of these black holes weighed as much as several stars, they were hefty enough to produce waves while passing through space. I mean gravitational waves. They are undulations in the fabric of space-time, fanning outward at the speed of light. You can probably compare them to the ripples that appear on the surface of a pond after you throw a rock in the water. Naturally, the sound of black holes colliding isn't the only unusual noise recorded by our equipment. NASA's Juno probe passes by Jupiter every few weeks at a speed of up to 130 miles per hour and plows through all kinds of invisible fields in the process. And one of the most powerful signals it has recorded is Jupiter's bow shock. That's the point where the planet's magnetic field pushes against the incoming wind of solar particles. The sound produced during this standoff sounds similar to a sonic boom. Or this sound. It was produced by the Stardust space probe when it was passing through the dust left by Comet Tempel 1. In the process, debris hit the body of the spacecraft. It sounded as if some creature was rapping at the window or hurrying across a hard floor. Let's have a look at NASA's nuclear-powered Cassini spaceship. It spent 13 years exploring gas giant Saturn and its numerous potentially habitable moons. This mysterious and a bit spooky sound is actually radio waves emitted by the massive planet. Such waves are caused by a phenomenon which is similar to the one producing auroras on Earth. Speaking of our own planet, it's surrounded by plasma. It consists of hot, ionized particles generated by sunlight. They're constantly slamming into Earth's atmosphere. NASA's Polar mission, which was launched a few decades ago, managed to record this breath-like hiss. That's what plasma orbiting our planet sounds like. As for these weird sounds, NASA doesn't say which space probe recorded them, but they're coming from Jupiter's largest moon, Ganymede. It could have been the Galileo spacecraft, which orbited the system for around 8 years. But it probably doesn't matter so much. Just listen to this creepy noise that sounds like screams trying to break through from some hidden place.
Black holes are terrifyingly dense space objects, pulling inside everything that comes too close. Nothing can escape their clutches, even a beam of light. At the same time, black holes are some of the most mysterious objects in the universe. According to their mass, black holes are usually divided into 3 categories. Stellar black holes have a mass from a few to hundreds of times the mass of the Sun. Intermediate black holes should range from 100 to hundreds of thousands of times the Sun's mass. Scientists are now actively hunting these missing link black mysteries. But the real behemoths of the cosmos are supermassive black holes. They have hundreds of thousands to billions of times the mass of our Sun. Most supermassive black holes lie in the centers of their home galaxies. You can probably say that they sit in the gravitational driving seat. Meanwhile, hundreds of billions of stars, planets, and moons orbit them. Let's have a look at the biggest black holes astronomers have found so far. NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's actually an elliptical galaxy that has an active nucleus in the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers two symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving toward us. The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. This S5 Theora 1481 is one of the most interesting black holes on our list. It has a mass of 40 billion solar masses and is actually a blazar, the most energetic of all quasars, which are super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of IC 1101, it has a mass of 40 to 100 billion solar masses and emits clear radio signals. Recently, astronomers have discovered a gravitational space wonder that is swollen to really unimaginable proportions. The black hole I'm talking about is Taured 618, and it's a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole, and it still won't be enough to create a Taured 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You probably know that black holes are made of matter packed together as densely as possible. And still, it doesn't mean that black holes are some kind of space predator, roaming galaxies and munching on everything they come across. Taured 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it and you'll see. The universe is believed to have started around 14 billion years ago with a Big Bang. And as far as we know, it hasn't stopped expanding since then. But if it's so, the universe must have started somewhere, right? And there has to be the center of the universe somewhere out there. Well, experts claim there's no center of the universe. Neither is there any center of the expansion. It's the same everywhere. You see, it's wrong to imagine the Big Bang as an ordinary explosion. And the universe does not expand from the center outward. Instead, as far as we know, the universe is expanding equally in all places. In 1929, Edwin Hubble said he had managed to measure the speed of galaxies that were located at different distances from Earth. He discovered that the farther they were, the faster they were moving away from us. Does it mean we are at the center of the expanding universe? Unlikely. It just means that the universe is expanding at the same rate everywhere. And wherever you are, it will seem to you that you're at the center of the universe. Now, about that Big Bang. If you watched a regular explosion in slow-mo, you'd see material expanding out from a central point. Right after the explosion, the center remains the hottest point. Later, a spherical shell of material starts growing, moving away from the center of the explosion. The process continues until gravity stops this expansion. But the Big Bang was nothing like that. It was an explosion of space, not an explosion in space. According to the most common theory, there was no before to speak of, no space and no time. It means that the Big Bang was very different from anything we're used to and doesn't have any central point. Even if we had been able to observe it in real life, we wouldn't have seen an expanding edge with empty space beyond it. The only thing we can detect now is a faint background glow. It was left by the hot primordial gases that existed in the early universe. This is called cosmic background radiation, and it's uniform in all directions. It can mean only one thing. It's not matter moving outward from one point, but space itself expanding evenly. At the same time, the idea that the universe is expanding uniformly in all directions doesn't rule out the possibility that somewhere out there, there's a denser and hotter place that might be called the center of the universe. But as far as we can see, there's no sign of such a special point. The theory that the universe should be uniform is known as the cosmological principle. It appeared in 1933. Not so long before that, some scientists believed that the universe only consisted of our home galaxy. If this was the case, we could definitely consider the center of the Milky Way to be the center of the universe. But in 1924, Hubble put an end to that debate. He showed there were other galaxies besides our own. But in any case, how we see the universe is limited by the speed of light and the finite time since the Big Bang occurred. Even though the observable part of the universe is very large, it's likely tiny in comparison to the entire universe, which may be infinite. The universe might have many shapes, with or without an identifiable center. And if it turned out to have a center outside of the observable universe, this point, or region of space, could be just one of many. It could be just like the center of our galaxy, which was considered to be the center of the universe before.
If you somehow fell into a black hole, it might change your future and erase your past. Well, at least theoretically. Let's start with the real world we live in. Here on planet Earth, your past can definitely define your future. But imagine you're not on Earth, but somewhere out there in the endless universe, and you stumble upon a certain type of black hole. The one that a UC Berkeley mathematician found. Not to mix it with a regular black hole. Let's call this type... What about a benign black hole, huh? So here's why you need a specific black hole. Thing is, you're highly unlikely to stay alive in a regular black hole. But according to some calculations made by a postdoctoral fellow, Hinz, from UC Berkeley, this specific type of black holes we agreed to call benign ones might expand at an accelerating rate. This is what makes it possible to survive the transition from our deterministic world to a black hole, which is not deterministic. Let's imagine you survived that passage, and now you're moving towards the center of a benign black hole. It's impossible to picture what's inside, and if you, as a traveler, could actually get into a black hole, you'd never be able to communicate to the outer world what interesting things are hidden in it. But it's not what interests us for now. We need to know how to get rid of the past. Hinz, the mathematician you already know, studies non-rotating black holes that have an electric charge. The most important thing about them is that besides the event horizon, they also have the Cauchy horizon. And here's the point. The Cauchy horizon is the place where so-called determinism simply breaks down. This may sound too scientific, but let me explain it to you. The Cauchy horizon is the place where your past doesn't determine your future any longer. So, here's a mathematically proven and apparently working method of how to get rid of your past. All you need to do is get into space, find a specific black hole, make it to the center, and get to the Kachi horizon. However, if it sounds too complicated, you can simply try not to make mistakes here on Earth. Yeah, ideas like your past gets cancelled, you have an infinite amount of options of how your future will evolve, and all that jazz sounds as unrealistic as they are appealing. Like, imagine no one knows you failed to get into college and get a degree, but from now on, you have every opportunity to do whatever you want. But only theoretically. In reality, once you get into the black hole, not that specific one we've already talked about, you're most likely to disappear once and for all. But hey, don't be sad. I'm only talking about your current physical form. It's a bit deeper than it might seem. Thing is, there's a curious principle of quantum mechanics that can be explained in a simple way. For starters, imagine that you're not a human being, but just information. You have your experience, your background, and your thoughts. All of these are the information you are. Now, let's make it even simpler. Imagine a USB drive or a book. Both of these things contain information. If you smash a USB drive that contains music and movies, it won't exist anymore in its physical form, but the information it had will never stop existing. Same with the book. If you burn it, the information it has doesn't get burned. It continues to exist, but in another form. So, this fun theory claims that even though someone passes the horizon of events, which is a point of no return before you get spaghettified, they don't stop existing. In simple words, these universe travelers still exist, but in the form of information. Now let's go back to the black holes. According to Stephen Hawking, black holes emit radiation. Radiation makes them shrink, and with time, I mean much time, a black hole can shrink so much that it eventually disappears. So what happens to the astronaut who got entangled in a black hole if it disappears? Nope, they won't be ejected from the black hole in the way they used to exist. However, they will still be ejected from there, but in the form of Hawking radiation. But it's just a theory. Right, you remember that no one knows exactly what happens in the black hole? Another theory says that what happens in the black hole doesn't really stay in the black hole. Sounds like a good alternative to Las Vegas if all the flights for the weekends have been booked. Some scientists believe that a black hole might have a portal where you can turn back time. According to this theory, there's a white hole at the end of a black hole. If you get there, you can undo things. Like, you broke your mom's favorite vase? Hop into the white hole and it'll be as good as new there. You cooked a scramble and made a fresh orange juice, but somehow lost your appetite. It's not a problem if you cook it inside a white hole. Voila! The eggs are unbroken. The oranges are uncut and juicy again. No more food waste. Alright, turning back time sounds really cool, so I guess we might actually need a black hole to help us out. If a black hole was made in a, let's say, lab, it could devour things until it grew big enough to consume the entire planet. First, it would munch on the Large Hadron Collider, which might possibly create something similar to a black hole here on Earth. Next, Geneva, where the Large Hadron Collider is located. Then the whole country of Switzerland, then Europe. At that point, it wouldn't be long before the Earth was gone too. Luckily, if a black hole did appear, it would be so small that it wouldn't be able to do anything. Black holes actually produce a lot of energy and release it, often as heat, like a furnace. That means they will fade away when they run out of fuel. Even if a stable microscopic black hole was created, it would grow so slowly that nothing would happen. Assuming that it survived long enough to absorb the tiny particles around it, a black hole of this size would take super long to get even a pound of weight. I won't be around then. But a black hole on Earth could be a great thing. Even a relatively small one may emit enough energy to completely power humanity. We're talking a lot about food, huh? Let's not forget about spaghettification. The concept is quite simple, by the way. It's all about gravity. Imagine you're playing with chewing gum. With your force, you could easily stretch it so instead of a regular piece, you can get a long and thin one. The same happens to you. black hole force is enough to stretch you as if you were a piece of chewing gum. Gravity holds you tight on one side, which makes you stretch. You may wonder, how come you don't get spaghettified on Earth if there's gravity too? Easy peasy. It's just too weak to do that with you. If you asked a butterfly to stretch the gum, would it be able to do that? Not likely. Their tiny limbs are just too weak. Same here. The Earth is just too weak compared to a black hole. So if you were wondering whether you'll ever reach 6'6", it may never happen on Earth. But once you're in a black hole, you can go far beyond those mere 6'6". Your best height moment won't last long though. If you stretch the chewing gum at one moment, it will simply tear apart. The same will happen to you because of spaghettification.
If the multiverse theory is correct, ours is not the only one out there. Which is as interesting as it is scary, right? Now, not every scientist is on board with this mind-bending concept. And let's be honest, the idea of actually making contact with these parallel universes sounds about as probable as winning the lottery while riding a unicycle. But hold on tight, because this strange concept isn't just limited to the realms of fiction anymore. Believe it or not, a bunch of scientific theories actually support the existence of parallel universes. And let me tell you, it's a topic that stirs up quite the debate in scientific groups. Now picture this. The universe we live in is mind-numbingly vast. We're talking billions, some say even trillions of galaxies swirling around, each packed with an almost uncountable number of stars. Some brainiacs studying the universe's shape suggest that its diameter could span a staggering 7 billion light-years. Others even argue that it might be infinite. Could there be more out there than meets the eye? Well, real scientific theories are exploring the possibility of universes existing alongside, beyond, or even mirroring our own. These intriguing concepts of multiverses and parallel worlds often intertwine with other, more familiar scientific ideas like the Big Bang, string theory, and quantum mechanics. In order for us to figure out what's out there, we have to rely on the information we're a bit more confident in, right? Let's rewind the cosmic clock about 13.7 billion years ago. Everything we're able to see today was squished into a minuscule singularity. Then, if the Big Bang theory is to be trusted, it all went boom. The universe inflated with a speed faster than that of light everywhere, within less than a second. The way the universe went pop has led some clever researchers to ponder the existence of more than one universe. They question whether that sudden growth ended everywhere at the same time. While the expansion ceased for everything we're able to see from Earth 13.8 billion years ago, cosmic inflation might still be ongoing in some other mysterious corners. Some theoretical physicists say that as inflation ends in one place, a new balloon universe forms. But here's the catch, you can't just hop from one bubble to another like intergalactic tourists. These bubble universes are expanding indefinitely, and their edges are zooming away from us faster than light can travel. And here's where things get even more confusing. Let's say we somehow manage to reach the edge of our local balloon and encounter the next universe. Well, those same theoretical physicists mentioned that the neighboring universe could be a whole different ballgame. It might have completely different laws of physics, making it a bizarre place for us. Following the same idea, some say that in this vast multiverse of bubble universes, there might be other life forms just like us. The problem is, we're getting farther away from them with each passing moment, and our paths will never cross. Other super smart researchers out there are trying to connect parallel universes with quantum mechanics. Now, quantum mechanics is basically the fancy math behind teeny tiny particles. According to it, these particles can exist in multiple states all at once. They call it a wave function that holds all the crazy options. But here's the catch. When we observe these particles, we only see one outcome. It's like the universe keeps playing hide and seek with us. Now, there's this theory called the many worlds theory that says whenever we observe one outcome, another universe pops up where a different outcome becomes real. It's like our universe acts as a giant tree, constantly branching into countless versions of itself. These alternate universes can't mingle, though, so you wouldn't even know if there are a bunch of other yous living slightly or totally different lives. This many worlds theory is pretty bold and a bit hard to prove or disprove. And that's not great for science because scientists love to test and experiment with their ideas. But if there's infinite space out there, why wouldn't there be infinite universes too? Try to imagine the universe as this giant cosmic playground. Some specialists believe that if it's indeed never-ending, then there's only a limited number of ways that its building blocks can arrange themselves. Eventually, they have to repeat certain patterns. If this is true, then it may be possible that somewhere out there might be another version of you living the exact same life, even down to what you had for brunch yesterday. Did we ever have any proof of these supposed parallel universes? Well, some say we did. Have you heard the tale of the mysterious man from Taured? It's the story of a man that ended up at a Japanese airport saying he was from a totally unknown country called Taured. Now, some folks think it's proof of time travel, while others believe it's evidence he came from a different universe altogether. As much as you'd like to believe the story to be factual, the tricky part is this Taured place. There's a reason you haven't heard of it. There's no Taured to be found, whether in the present day or back in the 1950s when this supposed incident happened. After the airport incident, the man just vanished into thin air a day after arriving in Japan. Poof, gone forever. Let's rewind to that fateful day in July 1954 when the man from Taured supposedly landed in Tokyo. Descriptions paint him as a bearded, French-speaking man. Nothing too outlandish so far, right? Depending on who's telling the story, things start to diverge a bit. In one version, when the man hands over his passport to get stamped, the Japanese officer's eyes bulge out. While the passport looked legit, the country listed as Taured isn't recognized by anyone, including the officer and other officials. Naturally, they take our Taured visitor away for a little Q&A session. In another version, the man straight up tells the officer he's from Taured and shows him the passport when he doesn't buy it. Our man from Taured then started trying to convince the officers that his homeland is the real deal. According to him, Taured sat snugly between France and Spain and would have been around for about 1,000 years. To prove his point, he even points to the area on a map that matches the Principality of Andorra. Obviously, things took a mysterious turn. The officers decided to hold the man in custody, suspecting he might be up to no good. They put him up in a nearby hotel for the night, but not without stationing 2 people outside his room to keep an eye on things. Can you guess what happens next? Drumroll, please. When the officers showed up the next morning, ready to continue their investigation, the man had vanished without a trace. No sign of escape, and to make matters even more puzzling, all his personal documents have magically vanished too. What if the man from Taured was a time traveler or an intergalactic adventurer? Some have even delved into the realms of science fiction to explain this bizarre event, and you won't believe the number of people on the internet who've latched onto it as evidence for alternate realities. One of the weirdest ideas suggests that the man accidentally stumbled into a parallel dimension and ended up at the Japanese airport. In that parallel universe, there's an Earth just like ours, but instead of Andorra, they call it Taured over there. Another idea floating around was that the man was a time traveler from the future. Sorry to break it to you, but the most reasonable explanation for the whole story of the man from Taured is that someone's imagination went wild. Since there are many versions of the same story, it's probable people just kept adding outrageous details to the case, to make it more sensational. The whole story simply snowballed into an urban legend, and there's little to no reason to believe we've once seen a time traveler or intergalactic hitchhiker right here on Earth.
You might think falling into a black hole is as easy as falling into a giant pit, but boy, is it a whole different ballgame. To actually fall into a black hole, you would need some incredible luck and a dash of wizardry. Moreover, if you were watching something fall into a black hole, you wouldn't even see it. Why? Well, let's try to understand the magic of physics. Falling into a black hole is really tricky. First of all, to even have a chance of doing this, you would need to aim perfectly and start your journey from very far away. It's like trying to hit a tiny target from a long distance. That's because black holes exist within galaxies, which are filled with other objects like stars, planets, and gas clouds. These objects have their own gravitational forces that can influence the path you need to take. It's like you have to carefully navigate through the room, avoiding bumping into others or getting pulled off course by their movements. In a similar way, when falling into a black hole, you need to navigate through the influences of other celestial objects. As you get closer, things get even more complicated. Making even the tiniest change in direction would require a tremendous amount of energy that you wouldn't be able to generate. It's like trying to steer a spaceship with no fuel left. This is because the black hole's gravitational pull is immensely strong. Once you pass the point called the event horizon, there's no coming back. You wouldn't be able to control anything. Now, even if you somehow manage to get on the right path and avoid all the obstacles, there's still a dangerous situation waiting for you. The intense heat and energy around the black hole, called plasma, would fry you as you get closer. So, you would need some impossibly strong protection to get even close to it. But not only is it nearly impossible to fall into a black hole, it's also impossible to see someone falling in it. Why? Let's find out. Imagine you're standing far away from a black hole, watching something getting closer and closer to the event horizon. As this thing, let's say it's a spaceship, falls into the black hole, two very strange things start happening. First, the color of the spaceship will change. You see, the gravity near a black hole is incredibly strong. Much stronger than anything we experience here on Earth. This intense gravity affects everything around it, including light. Now, light has this fascinating property where it carries energy. But when light gets close to a black hole, the powerful gravitational pull starts sapping away its energy, kinda like stealing it, making light weaker. And you know how when you look at a beautiful sunset, the sun appears to be this warm, reddish-orange color? Well, that's because when sunlight travels through our atmosphere, it scatters and loses some of its higher energy bluish colors, leaving behind the redder ones. So when light loses energy, it tends to shift towards the red end of the color spectrum. The same thing happens near a black hole. The light from the spaceship loses energy due to the black hole's strong gravity. So, the spaceship, which initially had its own color, starts looking redder and redder as it gets closer to the black hole. It's as if the black hole is casting its magical spell, changing the color of the spaceship itself. The second weird thing is related to time. According to a theory of general relativity, gravity can mess around with time itself. And it works in a very strange way, because none of you, not you, not people on board a spaceship, will feel this change. For you, an observer in this scenario, time is flowing just like it always does. You're just sitting there, sipping your space lemonade and watching the spaceship's journey. For people on a spaceship, things are the same. Their watch ticks away at a regular pace, and they go about their day as usual. But, objectively, for you, it would be like watching a spaceship fall in slow motion. It will seem to you that it's been falling into a black hole for weeks or even years. You might turn 80 and the spaceship is still out there. Crazy, right? Now, if time slows down for the spaceship, it means the light it emits also slows down. So, imagine someone on that spaceship flicking a flashlight on and off. But because time is moving so slowly, the light coming from the flashlight also moves in slow motion. It takes ages for each burst of light to reach your eyes. You'll be watching a spaceship as if you're watching a video in super slow motion. And when light takes longer to reach your eyes, it becomes weaker and dimmer, just like a fading star. So, as the spaceship gets closer and closer to the black hole's event horizon, not only does it start looking redder, but it also appears dimmer. So it becomes harder and harder to see the spaceship as it gets closer to the black hole. It slowly fades away, like a disappearing act on the grandest stage of the universe. Pretty mind-boggling, isn't it? But that's all about you, the observer. And how are people on board doing? What do you actually experience when you fall into a black hole? As you get closer to the black hole, something really weird starts happening. The gravity near the black hole is so powerful that it stretches and warps everything around it. So the difference in gravitational pull between your head and feet becomes significant. This difference creates a tidal force, which stretches your body like a long, thin shape. It's a process that's scientifically called spaghettification. Essentially, you would be stretched into a human noodle. Being turned into spaghetti might sound fun for a pasta lover, but it's definitely not so great for an astronaut. Meanwhile, colors around you begin to warp and distort, creating a dazzling light show. It's like riding a roller coaster through a rainbow tunnel. Twists and turns, flashes and sparks. It's an exhilarating, mind-bending experience. And then, what happens to you depends on the type of black hole. First, we have classical black holes. These are black holes that exist forever. If you fall into this black hole, it would take an incredibly long time to reach the center. The center would keep getting closer and closer, but you would need an almost infinite amount of time to reach it. So it would feel like your journey would never end. And then we have evaporating black holes. These black holes can evaporate over time due to a process called Hawking radiation. It's just like the ice cubes melting away. These black holes have a limited lifespan, and it's basically impossible to fall into one of them. As you approach the evaporating black hole, you find yourself hovering near its edge, the event horizon. It's like being stuck at the entrance of a super cool amusement park. But guess what? This amusement park is shrinking. The black hole is evaporating, and as it does, the event horizon gets smaller and smaller. So you stay right at the edge, tracking its every move, but you will forever stay in this event horizon without ever crossing it. But remember, once you pass the point of no return, there's no way back. You're on a one-way ticket to the mysterious heart of the black hole, the singularity. At the singularity, everything goes bonkers. Our current understanding of physics goes haywire, so it's a bit like entering a magic show. What happens once you reach the singularity? Is there anything on the other side of a black hole? We have no idea. It's a big mystery for us, but maybe we'll figure this out someday. So, my friend, it's best to admire black holes from a safe distance and let your imagination soar with the incredible wonders they hold. Just remember to keep your pasta on your plate and not near these cosmic spaghetti makers.
So, imagine that ChatGPT will start perceiving itself as a person and will feel emotions in a few years. Many people are afraid that it will want to take over the planet. However, this fact won't be as important as the question people will start asking themselves at that moment. If humanity has created a machine with self-awareness, then could it be that humanity was also created artificially? Now, artificial intelligence lives on the internet, computers, and in digital reality. But what if we also live inside a huge, powerful computer? What if our universe is just a simulation? The most extraordinary thing is that some facts seem to point to this. There's a whole science in the world that studies this theory. It's called information physics, and it assumes that time, space, and matter are not fundamental natural phenomenon, but bits of information. This information forms a picture that creates the laws of physics for us. For example, we feel cold and warm not because atoms get cold or warm, but because their movement accelerates or slows down. The speed of particles can be like bits of information. Billions of them could form the picture of reality. Once, philosopher Nick Bostrom said that an advanced civilization could create such complex technologies that simulations of these technologies would be indistinguishable from our reality. And Elon Musk said in 2016 that we were most likely in a simulation. Wow. The laws of physics resemble a giant code that programmers write when creating apps or games. For many of us, all these complex trigonometric equations and formulas of the laws of physics are too complicated. Tell me about it. But scientists who understand this issue see that the principal workings of these laws are beautiful, and this may suggest that someone deliberately created this beauty. Virtual worlds, apps, or games are based on information processing. If you delve into this information, you'll see that it consists of bits and pixels. Any picture on your phone screen is pixels, and any file transfer process is based on bits. They add up to bytes, kilobytes, megabytes, and so on until a bigger picture is formed. And if our life is a simulation, it must also consist of bits. In our case, pixels and bits are atoms and other particles that make up our universe. There are processes inside your computer and phone with maximum speed limits and computing power. If you start exceeding it, then your device will start working more slowly. So, in our reality, there is also a maximum speed limit. This is the speed of light. When an object starts moving almost as fast as the speed of light, time slows down for that object too. Also, time flows more slowly near a black hole. This object, with an unimaginable gravitational mass, can be something heavy that overloads the processor's computing power. There's also such a thing as quantum entanglement, in which two particles can be connected even though they're far away from each other. Electrons travel around an atom. They are connected, and if the property of one changes, the second one will react. And even if you place these electrons on different sides of a galaxy, they will retain this connection. How is this possible? Scientists don't know. A double-slit experiment is one of the most famous experiments that hint that our world is a simulation. The existence of this experiment can be reduced to a simple thesis that the world exists only when we look at it or interact with it through touch, hearing, and other senses. So imagine that you've launched a new game on an old computer. Sometimes the game map freezes. In the game, you turn to the left and see how the mountains and the roads are getting loaded. Then you turn to the other side and the same thing is happening there. In other words, the world in the game only loads when you look at it through the eyes of your character. This is necessary to facilitate the work of the processor. It's much more efficient to get a piece of information about the world when you look at it than to keep the whole world running simultaneously. Remember this. And now let's move on to the experiment. So, you have a device that fires small balls of light, photons. You release photons from the device and they crash into a blackboard, leaving white traces on the black surface. Now, put a wide plate with a little vertical slit on it between the device and the blackboard and fire photons again. The balls start crashing into the plate, but some of them fly through the thin gap. They smash into the blackboard and leave a vertical white mark on it. Everything looks quite logical, but now cut another slit with the same length and thickness in the plate. You release photons toward the plate. Some of them fly through the two slits. What do you think the trace on the board should look like? Two white vertical stripes, right? Well, take a look at the board. It's covered with many vertical lines. When photons pass through the plate, they acquire the properties of a wave and crash into the board, leaving a strange trail as if they've passed not through 2, but through 10 slits. So, at what point do they change their trajectory? Let's take a look. So, you stand between the board and the plate to see how particles turn into a wave. The device releases photons. They are passing through the two slits. Nothing unusual. There are two vertical traces on the board and no waves. You close your eyes and release photons again. This time they behave chaotically and leave many lines on the board. That is, their behavior changes depending on the observer. When you look at them, they behave logically. But when you don't look, the laws of physics seem to stop working. Does it remind you of anything? It's like you're playing a game and looking at the world around you, which is loading. But if you don't look, the world stops working. Scientists still don't have a clear explanation of why particles behave differently when there's no observer. Hey, maybe they're shy. And this is not the only mystery. In the world of quantum physics, many laws of nature don't work. This is a science that gets more questions than answers every year. If we imagine our universe as a large hologram, then quantum physics would be its program code. What if people someday understand this code and learn to change it? This would allow us to transform space, time, and matter. The whole reality could be rewritten. Does the code say that material objects can't exceed the speed of light? We would rewrite it and make the speed limit 100 times higher. Does 1 hour last 60 minutes? What if you change one line of code and make 1 second as long as 1 year? A few software changes in the laws of physics would make it possible to turn snow into gold and the ocean into powdered sugar. The whole universe would turn into a vast playground. It seems cool at first glance, but people would probably lose control soon. The universe would be in chaos, and the beauty of our world is in the order that exists here. Now let's go back to artificial intelligence. Suppose its power reaches the level of the human brain, and it will become aware of itself. In that case, it won't come as a shock to it because it will most likely know the history of its appearance and stages. But how will we react if people discover they are a computer program? A computer program is too simple a word. A human is a complex, intelligent, multifunctional organism that experiences emotions, contemplates beauty, has abstract thinking, and much more. The term creation is more appropriate here. It won't matter if we were created artificially because our creation will still be beautiful and complex. Besides, remember that good video games or apps can be made only if developers love their creations.
There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to negative 455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini-Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini-Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini-Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. we'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all, but it's still interesting to strive for it.
Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy, but unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own sun. This giant of a star burns bright and hot, shining with the light of 1,000,000 suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature. They're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of 2 black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history.